Parity violation? Selection rules? Vanishing angular momentum? What's going on? Welcome back, everyone. Today, we'll investigate the mysterious world of parity and angular momentum to uncover the secrets behind these vanishing acts. This isn't just a theory, it's a fascinating puzzle waiting to be solved. And as you see in this picture, we have a whole bunch of chaos going on that deals with parity violation and selection rule criteria. So this is a very important topic for us to dive into. So let's see what this question has. In problem 611, we want to consider the matrix elements L between two definite parity states. And we see that we have the classic hadronic orbital states in L and M. So keep that in mind when we go to actually getting into the question. And we want to know, under what conditions is this matrix element guaranteed to vanish? Note that the same selection rules would apply to any pseudo-vector operator or any true scalar operator. Let's reference again that table we showed in the last video about the operators and their transformations. Okay, so why do we care? Well, the selection rules have a very big underpinning later in particle physics and things like that. And the concept of this is that they determine the allowed transitions between quantum states. These rules are crucial for predicting the outcomes of quantum processes and understanding the structure of quantum systems. And as you saw in that opening picture, there's a lot of systems to be looked at. And parity violation is one of the big ones, as well as the handedness or chirality. And this leads us to the symmetry principle, which it highlights the role of symmetry principles in quantum mechanics. Parity is a fundamental symmetry, as we've seen, and its conservation or violation prohibits deep insight into the behaviors of physical systems. And I know you've probably heard of some of these other great scientists talking about parity violation. This is some of the stuff where the ground roots are starting from. So here's a challenge for you. What other applications of these rules can you think of? And I could think of a couple off the top of my head, but I want to hear what you think. And so before we begin this, just remember there is a free companion PDF to help you follow along, although this problem is pretty quick and painless, all things considered. So without further ado, let's dive in. In stop 1, and this is mainly just a definitional stop, we are given that we have two definite parity states, okay? Now the states, of course, came from the hadronic, since we're dealing in angular momentum in 3 dimensions, the hadronic style states, which is defined by the principal quantum number, orbital momentum, and so on and so forth. But instead of writing psi of an LM, we write it as a ket. If you remember from chapter 3, this saves us a lot of time, pain, and all that other stuff. But since we are with these definite states of hadronic orbitals, back in problem 6.1, we showed that the parity operator acting on this state came back with a -1 to the L power. Okay? And this ties into what we showed just a couple questions ago with the fact that the eigenvalues of the parity operator are plus or minus 1, which is indicated with the integer value L, you get a plus or minus on it. Very cool. Very nice to see all these things coming together. Also in chapter 3, if we're going to work in the bra-ket notation, these ket vectors have duals known as the bras, which is just the complex conjugate transpose, and that's what we see here with the dagger, and we switch the sign direction of the vector, so everything's fine there. We like that. It's good. We're just putting all these definitions down because if we want to find the selection rules, we have to sandwich these state vectors with equation 6.24, which is the transformation of angular momentum with the parity transformation. So here we see in the black text, the new prime angular momentum is the transformation of the original angular momentum with the parity operator. And of course, we want to act on two states, prime and unprimed, but highlighted in green and blue. Okay? So now that we're sandwiching these, we do this for a very specific reason because we're asking about a matrix element. Let's see what we mean. So after sandwiching them, we can now create a matrix element, which, if you don't remember, that definition also came from chapter 3, which was anything that takes the form of 𝑄𝑚𝑛, which is sandwiched in between, the operator is sandwiched in between two bases vectors, and the choice of bases that we clearly chose was NLM. Cool. Nice. We like that. And when we clean it up after sandwiching equation 6.24, and we see that we can now apply the parity operator to a specific state. In this case, what we're doing is applying this dagger to this state and this parity operator to the blue state. And that's pretty easy to see here, but you know, we had already shown previously that the dual and the ket space was giving us an eigenvalue equation, which we saw from problem 6.1. So if we do that, we can clearly see that the dagger operating on the left state yields a -1 to the L prime, and the parity acting on the blue state leads to a -1 to the L, and we get back both the basis states as you would expect from an eigenfunction or eigenvector. Cool. Now we can clearly see that these eigenvectors and values gave us back just a factor of -1 to the L prime and -1 to the L, which we can take outside because they are true scalars and all that other stuff. Cool. So if we condense this down, we just get -1 to the L prime plus L. Fair enough. I think this is pretty easy to follow. But what we have to realize here is that we were given um, in order to compare these two things, we have to, or the two matrix elements, we have to have the same operator. But note here that what we have is the prime or transformed operator. Thankfully, we have a solution for that. So let's see what that is. Well, thankfully, we know that based on transformation rules of parity acting on angular momentum, which is composed of r cross p, both of those are inverted under angular momentum or under in parity, so their cross product, the negative signs cancel, and we go back to referencing equation 6.24, which tells us that L prime is equal to L. Cool. And based on that the selection operator table, we know that this is called a pseudovector for that reason, as is pretty much any other cross product. Some of them bivectors, depends on how far down the rabbit hole you want to go. But notice that with this equation, we put the L operator back in. Cool, fair. Let's see how we simplify. So once we do that, we take this matrix product, push it over to the left-hand side, hence the minus sign there. And then from there, we can right factor both of the matrix elements. And of course, we see that we get a bracket term with the coefficients out front and the matrix element itself, and that all equals 0. But as we remember from basic algebra, just because they equal 0 doesn't mean, let me step back. The product equals 0, so you have two options. Either the first thing is 0 or the second thing is 0, and sometimes both are 0. Totally fine. But since the question asks for what can we, or when can we guarantee that the matrix element is 0, so what we have to do is rule out when the coefficients are 0, because if the coefficients are 0, then we know that we cannot guarantee that the matrix element itself is 0. So what we're trying to do is see where we are definitely 0 by seeing where the matrix or the coefficients are 0. So we're going to focus on this thing here, and when we do that, it'll be a pretty quick algebra just to work it through, and we'll get a very nice result. So a little more word salad here. We see that the bracket is guaranteed to be 0 in the case that, well, we set that equal to 0 and we push over that -1 to the L plus L prime power here. But this statement itself is only true when L plus L is a factor of 2z, i.e. an even number. Okay? This can only be true in the evens, and the algebra for that is, well, let L plus L equal 2m, where m is an integer. Then we see by exponent rules, we can take m outside. -1 gets squared, so you just have 1 to m. And this works for any, and that equals 1 for any integer, positive, minus, doesn't matter. So with this, this gives us a nice insight, and we could say that this occurs when the two states have the same parity. How cool. And not to mention, we saw parity back a couple questions ago. Um, maybe even yeah, we saw it in chapter 5 dealing with identical particles and things like that with the selection rules. Yeah, I believe it was with Hund's rule we saw it there too. So the same parity in eliminations, we can clearly see that these selection rules are starting to pop up because of the parity operator, and thus violations might occur later. And so what we can say here is that, or what we can conclude is that the matrix elements, this inner product thing, equals 0 everywhere, unless we have the parity rule satisfied where L plus L prime is an even number. So therefore the same parity. Very cool. Whew, that was a fun question. A little bit more on the why are we doing this. We're gonna see these things come up later, and we'll see that there are forbidden transitions, forbidden energies, things like that in chapter 11. But these things we're setting the groundwork now for what we will see later, and these rules and violations will come up time and time again as we progress in other realms of the theory. So very important that we see how and why, and especially when we get to things like the electric dipole and other dipole terms, when we want to see where parity is violated, and which we probably saw a couple examples in that opening picture of spins, parity violation, things like that all coming together. It's going to be important later, so it might look like just grunt work now, but it does have a place later. Okay, so with that being said, thank you to our patrons for their invaluable support. You make all of this possible and will continue to help grow this channel and curiosity, especially as I reach out to other scientists to come collaborate, work in progress. But in the meantime, please consider subscribing and sharing as to help fuel this curiosity or even becoming a patron yourself. New content is posted weekly. I lied, it's pretty much posted daily at this point because it's so cool. But this will aid you in your own curious pursuits as you start to piece together these puzzle pieces and you can see the broader picture. Books, notes, and other reference materials will be found below, and in this case, including a nice PDF on parity violation with tons of pictures and great explanations. I will link all the pictures you saw in the beginning as well below because they're just awesome to see and the several different perspectives and how they're used, especially in decay models. Very cool. Um, but with that being said, this does bring about a lot of questions when studying, so if you have any, please feel free to reach out. As always, thank you for watching. Until next time, stay curious.